What's up, guys? Welcome back to another Algebra 2 lesson here with Mr. Gaines. Um, we're taking a look at the QF.2 notes dealing with quadratic functions and their graphs. So previously, we looked at basically the key features of a quadratic function and how some of them come from the standard form of that function. We looked at standard form and how to find the y-intercept and the x-intercepts algebraically, and we talked about how to build functions given their roots or x-intercepts. Today we're going to expand on that knowledge and actually get into the graphing of quadratic functions. So I don't have my normal computer software here, so I'm going to do the best that I can to give you examples of graphs, but we're going to get to see the algebraic process that leads into graphing as well. So the first thing that we want to cover is the separate form of quadratic functions. We have standard form. We also have what's called vertex form. So vertex form of a quadratic function is when f of x is equal to a times the quantity x minus h squared plus k, where a, h, and k are all real numbers and a is not equal to 0. So this is actually a form that we've seen before. We've seen writing like this. We've talked about this back in the unit when we dealt with transformations. So we know that h is a horizontal shift, a translation left to right. K is a vertical shift, a translation up and down, and a is the vertical dilation. So you can see there on the diagram that I have the vertex listed as HK. And I told you I'd come back to that, and this is why. So the horizontal shift gives us the x coordinate of the vertex, and the vertical shift gives us the y coordinate of the vertex. So what we can do is we can add a little bit of information to this vertex form. So the vertex form is as written with vertex HK, and again where we know A is the vertical dilation. So let's actually take a look at how we're going to use transformations to help us graph quadratic functions. So there's a couple different ways we can graph quadratic functions. We're going to have the assistance of technology, but it's good for us to understand the concepts behind how the technology works to graph these functions, and to also understand how transformations work in the process of graphing quadratic functions. So let's go ahead and come down to problem number 3, where it says graph each of the following quadratics in vertex form. And so in 3a, we have f of x that is equal to the quantity x minus 3 squared minus 1. So what we can do here is we can use transformations to allow us to start this graph by finding the vertex. So I can find the vertex here by translating to the right or shifting to the right 3 from the origin. So I'd move to the right 3. And then in addition to that, I would also shift down 1. From there, I can go ahead and I can label a point. So this point would be, again, right 3 and down 1. So this would be 3, negative 1. This is going to be my vertex here. So from there, I can use the concept of a transformation or the concept of a quadratic to come up with my next points. So remember, with all quadratic equations or quadratic functions, they're parabolas, and with all parabolas, we have an axis of symmetry. So this dashed line will represent the axis of symmetry. Now, from here, basically what a quadratic function needs to do, it's an x squared value. So any horizontal movement is going to be squared to create vertical movement. So let's say I start at my vertex and I move right 1 unit. If I square 1, that gives me the amount that I'm going to move up vertically. So if I start here at the vertex and I move right 1 and I square that value, I'm going to move up 1, and that's going to be my new location for my next point. So that point would be on the x-axis. That point is 4, 0. Now if we go back to the x or to the vertex, and now I move right 2 units, 1, 2 units, I'm going to square that value to move up 2 squared, which is 4 units. So that point will be at 5, 3. From here, I can go ahead and do another point. So from the vertex, I'm going to move to the right 3 units. I'm going to square 3, and I would move up 9 units. So that point is going to be at 6, 8. Now notice that I only created points on the right side of the axis of symmetry. What I can do to get the rest of the points here is just reflect those points over the axis of symmetry. So now I have a point also at 2, 0. At 1, 3, and at 0, 8, which would be my y-intercept. Once I get these points, I can go ahead and sketch in my parabola. So that's a pretty rough sketch, but you kind of get an idea of what that parabola should look like. So the parabola should be a little bit of a curve. It should be more of a U-shaped than it is a V-shape. So we shouldn't have straight lines. It should be a little bit kind of a U there. So this is how we can use transformations to graph parabolas. Now let's take a look at another example. We're already again in vertex form. In 3b, we have h of x, which is equal to -2 times the quantity x plus 1 squared plus 4. So again, I'm going to start with my translations. I'm going to shift to the left 1 in this case and up 4. So I'm going to move left 1 and up 4. My first point is going to be at -1, 4. That is going to be my vertex. From here, I want to draw on my axis of symmetry. Now notice that this parabola, it actually opens down. So because I have this negative out in front of the leading coefficient, I have a vertical reflection over the x-axis. So this graph is going to open down. Thus, I'm going to have my axis of symmetry pointing down here. Now again, I'm going to need to plot some points from this specific point here. So if I go to the right 1, generally I would take that amount that I moved left to right and I would square it, and I would move down 1 in this case. But if we take a look at in front of the parentheses here, we have a 2, which is a vertical stretch. So it's going to double the distance that we move vertically. So if I go from my vertex point, I move right 1. Instead of moving 1 squared down 1, I'm going to double that distance. I'm going to move down 2 units for my next point. So my next point is actually at 0, 2. Let's go back to the vertex. If I move to the right 2 units, generally I would move down 2 squared or 4 units, but I'm going to double that and I'm going to move down 8 units. So my point is at 1, -4. So that 2 is doubling the distance that I would generally move vertically. From here, I would go back to the vertex, go right 3 units, 1, 2, 3. Generally, I would move down 3 squared units, but I'm going to go ahead and double that. And so instead of moving down 9, I'm going to move down 18, which would take me off my graph. If you want to put that point there, you can, but we don't have to. Let's go ahead, and now we have 2 points to the right of this axis of symmetry. Let's reflect that. So I'm going to reflect this point over the axis of symmetry, and I have a point at -2, 2. I'm going to take this point and reflect it over the axis of symmetry. I now have a point at -3, -4. And this gives me enough information here to go ahead and sketch my parabola. And there I have a rough sketch of my parabola, this time opening down. So what I want is I want that parabola to again look more like a U shape than a V shape. So here we have been using transformations to graph these parabolas. Now you can always type these graphs or these parabolas into your graphing calculator and then check the point locations with what you have in the table of your graphing calculator to make sure that you have these as accurate. Now let's go ahead and take a look at problem number 4. Problem number 4 is a little bit different because now we have quadratic equations that are given to us in standard form. So 4 says that given each of the following, graph the quadratic function by completing the square. So we learned the method completing the square when solving quadratic equations. We're going to use that method not actually to solve here. We're not going to completely solve the function, but we're going to use this method to rewrite the function in vertex form so that we can graph it using transformations. So what I'm going to do here first is remember that to complete the square, it relies on a couple things. Our leading coefficient has to be 1. We need this in standard form. And we need the c value to be a certain numeric value, which is b divided by 2 quantity squared. So what I'm going to do is I'm going to actually kind of ignore the 5. Generally, when we solve equations, we subtract the 5 and we would move it over to the other side of the equation because we would want to start fresh by getting our c value. Well, in this case, there's no equation, there's no other side, there's no 0 that it's set equal to. So g of x is going to stay there by itself. We're going to keep the 5 in the same location. What we can do instead of moving things around is we can actually group the first 2 terms. We're going to group the x squared and -6x. And then we're going to focus on completing the square with just the x squared and the -6x, kind of ignoring the 5 for right now. So I need to determine a b value that's going to work for x squared minus 6x. Sorry, a c value. So to find that c value, what I would do is take my b value, which is -6. I would divide that by 2, and then I would square that. And that's going to give me the value of 9. So what I want is I want a c value of 9. So how do I get that c value of 9? Well, what I'm going to do is I'm going to add it inside the parentheses, essentially here. So I'm going to add the c value of 9 inside the parentheses. So you see that here, I have x squared minus 6x plus 9. That gives me a polynomial that I can go ahead and turn into a perfect square. Now, what this does, though, at the same time as adding that 9 in, I've actually changed the value for this polynomial. So if I were to simplify this, this would be x squared minus 6x plus 9 plus 5, which would be plus 14, which is not the equation that I started with up here. So what I need to do is I need to make sure I take care of keeping the equation equal, not changing the equation. So in order to do that, if whatever I put inside of the parentheses adds or subtracts something to this equation, inside, in this case, I added 9 to the equation. Outside of the parentheses, I need to do the exact opposite action. So if I added 9 to the equation based on putting the 9 in the parentheses, I need to subtract 9 from the equation. So this keeps the equation balanced. So now if I simplify, this would simplify into x squared minus 6x plus 5, which is what we started with, okay? Now the reason I do this is so that I can write it into vertex form. Now if you remember completing the square, when you complete the square, you can set, once you have the perfect trinomial, this x squared minus 6x plus 9, that perfect trinomial, we can break that down into a binomial that's going to be squared. So the terms inside the parentheses would be x, because x squared is x squared, and -3, because my binomial here, the constant is half of the -6, but also the square root of positive number. So I'm breaking just down this trinomial that was in parentheses now into a binomial that's squared. In addition to this, I'm going to simplify outside of the parentheses. So 5 minus 9 would be a -4. Now, what this has done for me is it has turned this equation into a vertex form. And now I can graph my parabola. So we know how to graph in vertex form. The first thing that we're going to do is we're going to find the vertex. So the vertex would be found by shifting to the right 3 and down 4. So I'm going to move right 3, down 4 on my graph. There's my first point. Notice that this is a positive. It's a positive leading coefficient. So this is going to be a parabola that opens up. There is no reflection. So I have put in my axis of symmetry here. It is opening vertically. Now I can plot some more points. So if I look at points from the vertex, if I move to the right, I move to the right 1 unit, I'm going to move up that amount squared. So 1 squared is 1. If I move right 1, I'm going to move up 1. Notice there's no dilation here, so I don't have to worry about multiplying that number. If I move to the right 2, I'm going to move up 2 squared, which is 4. If I were to move from the vertex to the right 3, 1, 2, 3, I would move up from that location 3 squared, which is 9. And so now I have points at 6, 5, 6, 5, 5, 0, 4, 1, and then my vertex, sorry, 4, -3, and then my vertex 3, -4. Now I can take these points and I can reflect them about that axis of symmetry. And as I do that, I now have a parabola, or the shape, a basic shape of a parabola. And there we have a sketch of our parabola. So again, ideally we would like this to be a little bit more of a U shape than a V shape, a gentle curve. As you can see here with the electronics, it's a little tough to do, but you get the general idea of the parabola that we're looking for. Now let's go ahead and go over to 4B, where we're going to do the same thing, but we're going to see a different issue that we have to encounter. So here we have -2x squared minus 8x minus 4. So the same concept is going to carry forward. We would like to ideally start anew with the binomial negative 2x squared minus 8x and ignore that negative 4 for right now. So I'm going to go ahead and set up some parentheses around negative 2x squared minus 8x. Now, in order to complete the square with these terms, I need a leading coefficient of 1. And currently, we have that leading coefficient of negative 2 in front of the x squared. So what I need to do is then to go ahead and factor out this negative 2. So if I factor out negative 2, that's going to leave me with x squared plus 4x. So factor that negative 2 out of that set of parentheses, and I get x squared plus 4x. Now I can complete the square with what remains inside the parentheses. So ignoring everything else, I'm just completing the square with x squared plus 4x. And so I would find my c value here. C is equal to b, which is 4, divided by 2 quantity squared, so that's going to give me 4. So I need 4 inside those parentheses. So I'm going to go ahead and add 4 inside the parentheses. Now, what we saw previously is we added a 9 inside the parentheses and we did the opposite. We subtracted 9 outside the parentheses. That was because we didn't have any coefficient. So remember what this negative 2 does right here. This negative 2 multiplies to everything inside of the parentheses. So though we put a positive 4 in the equation here, in the parentheses, we didn't add 4 to the equation. What we really did was we added a negative 2 times 4. So technically what we did to the equation was we subtracted 8. We subtracted 8 from the equation. It doesn't look that way, but remember that leading coefficient is distributed to everything. So if I distributed, this is actually a negative 8 inside the parentheses. The value overall would end up being negative 8. So I need to do the opposite on the outside of the parentheses. I'm going to add 8. So it's not just add 4 inside the parentheses, subtract 4 outside. We can't just go with just that. We have to make sure that if there's a leading coefficient, we figure out what that effect is going to have on the 4 and do the opposite. So the negative 2 would turn that 4 into a negative 8. We need to do the opposite and add 8. Now we can simplify the equation. So h of x, we're going to put into vertex form. We're going to leave that negative 2 alone. Inside the parentheses, we are going to have x plus 2 quantity squared. And then we are going to simplify negative 4 plus 8 to get a positive 4. And so our function for h of x that we're going to look to graph is negative 2 times the quantity x plus 2 squared plus 4. And let me show that this actually is accurate. So we're going to graph this in a second. I'm going to show you how to use the graphing technologies to help us graph here. But let's say that negative 2x squared minus 8x was the function that we were intending to graph, and it is h of x. What the function that we came up with was negative 2 times the quantity x plus 2 squared plus 4. And if I compare those two graphs, we can see that those two graphs are exactly the same. So we have appropriately converted the equation here from standard form into vertex form of the equation. So we have to be careful there. We want to make sure that we complete the square, but you also have that graphing calculator, the tool there to help you verify that you've done the work correctly. Now let's go ahead and let's graph this. I'm actually going to go ahead and graph this by hand for some more practice. So we're graphing negative 2 times the quantity x plus 2 squared plus 4. So what we have here is a shift to the left 2. So x plus 2 would be to shift to the left 2, and then shift up 4. So left 2, up 4. There's our vertex. Now, we do have a negative out in front of this set of parentheses, which means we have a vertical reflection, so our parabola is going to open down. So there's my axis of symmetry, and I need to include some other points. So from the vertex, I'm going to move to the right 1. I'm going to move right 1 from the vertex. Generally, I would move vertically 1 squared, so down 1. But again, notice we have this multiplying factor of 2, so I'm going to double the distance that I move down. So instead of moving down 1, I'm going to move down 2. So my next point is going to be at 1, 2. Go back to the vertex, move right 2 units, 1, 2. I'm going to square that amount, which would generally bring me down 4, but I'm going to double it again because I have that vertical dilation, which would bring me down into 0, negative 4, the y-intercept. If I moved right 3, 1, to 3, I would square that value to get to 18, and then again double it because of my vertical dilation, move down. Sorry, I'd square 3 to get to 9, double that value to move down 18, which would come off my page. So I'm going to go ahead and finish these points off by reflecting what I have on the right side of the axis of symmetry to the left side of the axis of symmetry. And there I have the points that I can use to draw in my graph. Then there we have it. So there we have a graph of negative 2x squared minus 8x minus 4. So let's go ahead and let's scroll down and let's take a look at C and D. So in C, I'm wanting to graph r of x, which is negative x squared plus 2x plus 3, again by completing the square. So the first thing that I'm going to do is I'm going to take the first two, I'm going to take these first two terms and I'm going to group those together. So I'm going to group those together and then I'm going to try to complete the square with just this negative x squared plus 2x. We got to make sure that we have a leading coefficient of 1. So in this case, I'm going to need to factor out the negative. So if I factor out the negative, what that leaves me with is inside the parentheses, that leaves me with x squared minus 2x. Then with x squared minus 2x, I want to complete the square. So I'm going to go ahead and take a negative 2 divided by 2 and square it to come up with my c value, that is 1. So I'm going to add inside the parentheses 1, positive 1. That's the c value that I need. Now the trap again here to fall into, this is where people often make the mistakes. We have to be careful of what is actually that 1 inside the parentheses when we add that, what is that actually doing to the equation? So we have to take into account this leading coefficient. This leading coefficient is negative 1. So this negative 1 would get distributed to that positive 1, which actually makes it a negative 1. So it's, when I put that plus 1 in the parentheses, I'm actually subtracting 1 from the equation again because of that coefficient in front of those parentheses. So I need to do the opposite outside of the parentheses. I need to add 1. So here I can simplify my equation. So r of x is going to be equal to, still with that negative out in front, x minus 1 quantity squared. Make sure it is a minus 1. It's got to be half of that b value. Then plus 3 and plus 1 would give me plus 4. So now I can go ahead and I can graph this. So I'm just going to show you real quick how we would graph this using the graphing technologies. So if we want to graph this in standard form, we could type that in. We could also graph this in vertex form. So you would type these equations on your calculator, on your graphing calculator, which is what you'll have access to during the quiz, is you would type these equations on under the y equals portion. So y equals, then you type it in, and then you'd hit the graph. Now, another thing, we can see here that these two equations are the same as we wrote the vertex form and the standard form. We did do that correctly. Another thing that we can use here is the table. So if you go to second and then graph, that takes you to the table. It helps us to find points that we can graph. So we do want to make sure we find our vertex. Our vertex is 1, 4. Our vertex is 1, 4. It's a shift to the right 1 and a shift up 4. So we want a couple points on each side of that vertex. So I have 3 points that would be to the left. So 1, 2, 3 points that would be to the left of my vertex. I want 3 points to the right as well. So I'm going to take 3 and 4 down there. And if I'm using the technology here, now I have points that are given to me on my coordinate plane or my table that I can put on my coordinate plane. So I'm going to go ahead and take -2, -5. Sorry, I forgot to share my screen. You guys heard me talking, but didn't see the graph. There's the graphs. Sorry about that. I'm going to take -2, -5, and I'm going to graph that. Then I'm going to graph -1, 0. I'm going to graph 0, 3. I'm going to graph 1, 4. Then 2, 3. Then 3, 0. And then 4, -5. And there I have the points for my parabola. Okay, so that would be the same points that we would find if we found the vertex. And then I move right 1, I squared it, and I moved down 1. I move right 2, I square that, and I move down 4. move right 3 from the vertex, I square that, and I move down 9. All of those points would be in the same location. So at this point, we are ready to sketch our curve. Now, I didn't originally put in my axis of symmetry, but we would probably like to put that axis of symmetry in there just to make sure that we know that it is symmetric on both sides of the parabola. And again, as you sketch that parabola in, make sure that it's a little bit more U-shaped than it is V-shaped to make it look like a curve. Last problem here for today. Let's go ahead and take a look at D. What I want you guys to do at this point is to pause the video. See if you can complete the square here to come up with an equation for Q of X that's going to be in vertex form. So go ahead and pause, and then you'll see if you get the same thing that I got. And here we have a graph and an equation for Q of X. Hopefully yours looks the same as mine. So let's walk through what I did here. So initially I went ahead and grouped the first two terms, 3x squared plus 6x, so that I could complete the square with just those, again, ignoring that constant at the end, -5. We're going to use it, but we're setting it aside for the moment. Then I went ahead and I factored out the 3, because you cannot have a leading coefficient of anything other than 1 if you want to complete the square. So I factored out the 3, so what was remaining was x squared plus 2x. From there, I found the new c value that I needed. So my b is 2. I divide 2 by 2 and square it. That gives me 1. So I need the c value to be part of that trinomial, so I went ahead and added that inside the parentheses. So now inside the parentheses, I have x squared plus 2x plus 1, which is good. However, I have to make sure I did not change the equation. So I want to make sure I do the inverse operation of what happened to that equation when I added 1 inside the parentheses. What I did not do was add 1 to the equation. Because remember, this leading coefficient 3 would get multiplied to 1. So really what I added to the equation was 3. So I have to make sure I subtract 3 outside of those parentheses to keep the equation equal. And then I simplify. So that trinomial breaks down to x plus 1 quantity squared, and -5 minus 3 is -8. You can go ahead and compare graph the equation in vertex form to the equation in standard form and see if they're the same, and they would be, so we did do this correctly. Now in graphing this, I went ahead and found the vertex, and I actually graphed this incorrectly. So hopefully you have a different graph than what I have here. There, now we should have the correct graph. So again, when graphing, this would be a horizontal shift left 1. That was the mistake that I made originally. This would be a shift left 1 and a shift down 8. So that gives me my vertex, and I drew on my axis of symmetry facing vertically, going up because there is a positive leading coefficient. Then when finding my points, I have a vertical dilation of 3. So when I shift to the right 1, I square 1, which is 1, and then triple that distance and move up 3. When I go back to the vertex and I go to the right 2, I square 2, which is 4. I triple that distance, so I'm going to go up 12. Then reflect each of those points across the axis of symmetry, and there I have points to draw in my curve. Again, making sure that that curve looks more like a U than a V. And this looks like a pretty good place to stop. So at this point, we have covered one of the techniques for graphing quadratic functions that are in standard form. When we take a look at the next video, you're going to learn how to graph the functions using a much easier method that we call the vertex formula. In addition to that, we will talk about application problems and how we can use quadratic functions outside of the classroom. As always, thank you guys for tuning in, and I will see you soon.